The figure below shows two arcs of a circle on which plus q and minus q have been spread or squished or smeared uniformly. What is the value of the electric potential, voltage, at the center of the circle? Okay, so voltage is always a difference, and we're going to be comparing the center of the circle to infinity. And the general formula that we're going to use for this is the potential due to a point charge. So I'm going to say V is, I'm going to use something darker, just so you get better contrast. V equals KQ over R. This is compared to the electric field, which E is KQ over R squared. And one of the things is electric field is a vector, potential is not. So, interesting. Yes. So if we look at this potential right here, so the definition, another definition, equivalent definition, is the energy required to take a point charge, positive point charge, from infinity and move it here. And so that is going to be, so it'd be, as we're bringing this forward, it's going to be repelled by these charges right here, the positives, but it's going to be attracted by the negatives right here. And since it is symmetrical, I think this is going to be 0. So you're going to have just as much pulling from the negative charges as you're going to have repelling from the positive charges. So looking at this from a slightly more math point of view, I'm going to say that a small amount of voltage is K, small amount of charge over R, where R is uniform. To solve this, we'll take the integral of both sides. K over R, pull it out of the integral because it's uniform. And so we get K integral delta Q. So the voltage to the positive side is going to be K over R. And this is going to be, I'm going to call this positive Q, because if we integrate over the charges going this way, and we could do like from like 0 to pi over 4, pi over 2, or something like that. But we don't need to, because it's going to be all the charges. And then we do it from the negative side. It's going to be the exact opposite. So we still have K. We have the same radius, and it's all going to be the same R, because they're quarter circles. So that's going to be the same R for both of them. Q minus, so V total is going to equal V plus V minus, which they're the same except the opposite signs, which is going to equal 0. So the voltage at, supposed to answer in terms of Q, 0 Qs. So find what is the value of the electric potential? At the center of the circle. So electric potential is 0. This would be a different question if they asked for the electric field. The electric field would be a vector, so we'd have to do this a little bit differently. What would happen is the electric field from these, at this point, from the positive, the electric field goes away from positives. So we basically have from this point up here, from that point there, get them together, and we'd have a net electric field from the positives going that way. For the negatives, electric field goes in, so from here, go over this way, here it go down this way, combine the vectors, and we get electric field going that way. So the electric field at this point, though, would not be 0. When we added it up, it would be that direction, but we'd approach the problem the same way. We'd say that the electric field, a small bit of electric field, equals K delta Q over R squared. We do the integral of both sides. We can factor out the K and the R squared. And then we have to, we'd have to do like a sine cosine thing to find out everything that canceled, but it'd be totally possible as well. So that's how we do that problem. Kind of a trick question. And the way this question is made easy is because voltage is a scalar, not a vector, so direction does not matter, and it makes the integral be like, oh, okay, total amount of Q, total amount of charge, adds up, add a positive and a negative, and get 0. So I hope that helped. See you next time.